Hello, multivariable calculus students. This is Mr. Johnson, and this is the asynchronous video for section 11.7. And we're going to get into discussion related to maximums and minimums. And so we'll look at both local maximums and minimums as well as absolute maximums and minimums. And so this first video here is going to cover the first four examples. And the idea behind it is I want to give you a sense of what happens at an absolute max or min in space, and one of the tests that we'll use quite often with regard to how to analyze whether or not there is a maximum or a minimum. So you can look through some of these definitions that I've taken from our textbook. You can visualize based on all of the study that we've done of maxes and mins in single variable calculus, that in multivariable calculus it's very similar. We're looking for, in an absolute sense, the highest value or the lowest value on the z-axis as we analyze a surface. And in a local sense or a relative sense, we're looking at just a region, that is higher or lower in a particular surface or on a particular surface. And so the visual isn't going to really change anything. We are in space now, so that does matter. But really, this definition just describes the two different things when it comes to looking over a surface and analyzing some sort of change at a given point. We have a theorem below that is really the key to analyzing what's happening, and it really boils down to the same idea as we had in single variable calculus, where if you had a maximum or a minimum, you were to analyze the derivative, and if the derivative was either 0 or undefined, then you had a possible maximum or minimum at that point. We're really going to do the same thing, except in this case we're in space, which means we're going to look at the partial derivatives. Now keep in mind that you could either, and I'll add this in, you could either have a partial derivative that is 0, or it could be undefined, just like in single variable calculus, and that's true for the other partial derivative as well. Now the key here is that when we're analyzing a particular maximum or minimum, we want to analyze the partial derivatives together. It's not just one or the other, because if one partial derivative would be 0, for example, and the other one would not be 0, we're not going to have a local max or a local minimum at that point. So really what we're analyzing here is the gradient. So you can just think of this simply as the gradient vector, and what we're trying to figure out is whether or not the gradient is the 0 vector, or if the gradient is undefined. Now, almost in all cases in our class, the gradient will be 0, 0 at a local min or a max. We're not going to do too much with sharp corners or cusps. That would be where the gradient would be undefined. We're really going to focus our attention on a gradient that is 0, 0. And the test I'm going to teach you in just a moment here on the third example really is necessary when it comes to the first derivative, the gradient vector being 0, 0. Okay, let's look at a quick example. And you can see the graph over to the right, so this isn't a huge surprise or anything. But we have this equation f of xy, and we want to find the critical points. Now you can see in the graph that there is one minimum. It's 1, 3, 4. And we're going to find that the gradient at that particular point is the 0 vector. But I want to pretend like we can't see the graph right now. Let's just pretend like we're looking at the function itself, trying to analyze any of the critical points and whether they're maximums or minimums. So your first step is pretty simple. You're going to take the gradient vector, and in this case we get 2x minus 2 and 2y minus 6, and then we simply are going to analyze when the partial derivative with respect to x is equal to 0. That, of course, is when x is equal to 1, and when the partial derivative with respect to y is equal to 0, and that is when y is 3. And so what we have here is a value for x and a value for y that causes the gradient vector to be 0. Now in this case there is only one of those. This is how we would identify our critical point. And again, I know you can look at the graph and identify it, but if we didn't have the graph, this is algebraically how we would identify it. Now if you were to plug in 1 for x and 3 for y, you would get a z value of 4. And so our first task is complete. We have found the critical point. Now the question is whether or not that critical point is a maximum or a minimum, or possibly neither, which we have a name for. We'll discuss that in a minute. So in this case, what I would do is think about the equation itself. We have this equation, and I'll make this z equals x squared plus y squared minus 2x minus 6y plus 14. What if we were to complete the square? So what if we were to take x squared and group the x term together and complete the square? So we would add 1. And then we take the y terms and we complete the square by adding 9. Of course, we need to balance this out. So we need to subtract 9 and subtract 1. This is a similar process to what we have done with like an equation of a sphere or those types of things. So we have the quantity x minus 1 squared. That would be representative of all of that. And we have y minus 3 squared. That would be representative of all of that. And of course, over here we have 14 minus 9 minus 1. So we have just 4. And this helps us to slightly better analyze the situation. So for example, if you were to analyze x minus 1 squared, it is always greater than or equal to 0, as well as y minus 3 quantity squared. That really means that the minimum value of z is equal to 4, because if you minimize both those elements of x and y, you get z equal to 4. Now, when you think about the elements of x and y, they continue to grow to infinity, which means that there is no maximum to this particular graph, but there's clearly a minimum. And that's what kind of where we're sort of at in terms of our analysis at this point. I'm going to teach you a lot more as to how to really analyze this. But at this point, we would say, okay, well, this critical point, aside from looking at the graph right now, if we didn't have the graph, we would say that we would assume that this particular critical point would be a local minimum. However, it does appear as though it would be an absolute minimum as well, just because, you know, we're not finding any other values that are going to be larger than it. We kind of have a sense of the parabolic shape of this particular surface, and that's sort of where we would stop our analysis at this time. Okay, let's move on to the next example. All right, with the next example, I have the picture for you as well. Let's go ahead and go through the problem and analyze it in the same way. We're going to take the gradient of f, that gives us negative 2x and 2y. And same thing, we're looking at when the partial derivative is equal to 0. That means that x would be 0. Okay, we have the partial of y with respect to, or excuse me, the partial derivative with respect to y equal to 0. That's going to be y is equal to 0, so not super entertaining. Basically, that means that we have a single critical point, very boring point. It's going to be at 0, 0, 0. All right, that's our first task. We have one critical point. Now the question is the critical point a maximum, minimum, or neither? Now I know you can see the graph, and you can sort of get a sense of the behavior of it. One of the things that we could do, try to analyze this, is that we could analyze what this particular surface looks like on the YZ plane. And what I'm doing here is I am eliminating x. I'm making x 0 so that I can focus on a very specific level curve just to get a sense of what it looks like. Now, if you picture this, I'm really just analyzing this parabola right here. Okay. Now, the way that we could do this algebraically is we could just take our equation, which is z equals y squared minus x squared, and simply plug in x equal to 0, which means we get y is equal to, z is equal to y squared. And this would imply that 0, 0, 0 would be a minimum. And we can see that. If we just look at this level curve right here, and we're looking at the point 0, 0, 0, that is clearly a minimum of that little parabolic trace. Okay, let's get rid of that, and let's look at a similar trace, except this time we're going to go on the xz plane. And that means that I'm eliminating y, I'm letting y be 0, z would be equal to negative x squared. Okay, so what I'm doing is I'm analyzing this, it's kind of behind here, but this trace right here. And you can see that this is also parabolic, but all of a sudden our point 0, 0, 0 is a maximum. And this idea is an issue, because when we're trying to figure out is it a minimum or a maximum, we need to make sure that it agrees with any trace that we would possibly analyze for the particular surface. So all of a sudden we took two very simple traces and we had a discrepancy between what we found, very distinct discrepancy and therefore this particular point is neither a max or a min. We actually are going to call this a saddle point, and you'll see that in the next example here. Okay, let's move on and discuss, it's kind of a large test that I'm going to show you here, but the idea is that we can't quite get by with what exactly we're, like our strategy at this point. Our strategy at this point is to try to do our best to analyze the surface, and we've had a couple surfaces that are relatively straightforward. However, we're going to have surfaces that are much more complex, and so the issue here is that we need a better system than just by observation, basically. And the system is called the second derivative test. Now, in single variable calculus, you learned about this test. Basically, this test said that if you have a particular graph, let's say you have f of x like this, and you had some point right here that was a minimum, okay? The derivative at this point is equal to 0 because the tangent line is horizontal, so the slope is 0. And in this picture that I drew very sloppily, this is a concave up portion of the graph, which means the second derivative is positive. And if we were to analyze these together in single variable calculus, that is called the second derivative test. It allows you to identify a relative max or min using the second derivative. The key is that you must know that the first derivative is 0 in order to use that test in single variable calculus. This test is very similar in multivariable calculus. We are going to do a series of tests. We're going to be utilizing the second derivative, and then we're going to be analyzing what is kind of like concavity. So I'm kind of analyzing concavity here, but let me just walk through the test really quickly, okay? So we're gonna assume that a function is twice differentiable. That all the partial derivatives of the first and second derivative exist, okay? Otherwise, you can't use the second derivative test. Also, the first derivative with respect to x is 0, and the second is with respect to x is 0. Keep in mind that all that means is that the gradient vector is 0, 0. It's the 0 vector. Okay, if that's true, then we calculate d. Now, d is a combination of analyzing the second derivatives with regard to x and y, with the second derivative with respect to xy, which again is equal to yx. That's Clairaut's theorem. And you use this formula to analyze the value of d, which allows us to analyze the behavior at this particular point. Now, if d is greater than 0, there are two situations that occur. So if d is greater than 0, you look at the second derivative both with respect to x. If it's positive, think of that as concave up, then the function has a minimum. If d is positive and the second derivative both with respect to x is negative, then think of it as concave down, therefore there's a maximum. If d is less than 0, then it's a saddle point, and I specify that right here, okay? If d is equal to 0, well, then we don't know anything. Now, if you want a formula to remember d, it's actually the determinant, and that's written down here at the bottom. When you think about matrices, and we talked about this before when it comes to the cross product, this is maybe a shortcut if you need that. If not, then go ahead and just memorize the formula. That's completely up to you. Okay, let's move on to the next example. Okay, let's go ahead and do example 3. So same kind of thing, we're just going to find the local max and min values for the particular function. We do have the surface graph as well as contour, so we'll talk about a little bit of that in a second. Let's go ahead and start with the gradient vector, and that will be 4x cubed minus 4y and 4y cubed minus 4x. So we have our equations. So we have the partial with respect to x equal to 0. Whoops. And then we have the partial of y with respect, or the partial derivative with respect to y equal to 0. Okay, and then we're just, we're kind of sitting with a system of equations here. We're just trying to solve for our variables as best we can. Keep in mind that as we look to solve, we have to use elimination or substitution, maybe a combination of the two. This section 11.7 as well as 11.8 is very much a systems of equations kind of solving techniques, and you have to sort of think outside the box at times. Sometimes it's going to be straightforward. Sometimes you're going to try something that's not going to work. You have to go back and try something different. So it really just depends on the type of problem for the strategy used. What I'm going to do for this one is I'm going to solve this equation. Let me think here for a second. Let's do this equation and solve for y. So if I move my y over, I get y equals x cubed, and then what I'll do is I'll just substitute that in for my second equation, okay? And that gives me 4 x to the 9th minus 4x equal to 0, so we can factor out the 4x. X equal to, let's see, hold on, sorry. We get x equal to 0 and positive or negative 1. I'm going to warn you about a common mistake that can be made when you come up with your critical points. You have to be really careful how the points are generated. So for example, if I have x equal to 0, and what we're doing is we're substituting this back in to one of our equations in order to find what y is. So if x is 0, I get y is 0. So as I start listing my critical points, I get 0, 0. That one usually is, I mean, in this kind of a context, that's fine. People aren't going to mess that one up. But here's where a lot of people mess it up. If I plug in x is 1, 1 cubed is 1. Therefore, 1, 1 is a critical point. If we plug in negative 1 cubed, we get negative 1. Therefore, negative 1 is a critical point. But then here's what people do is that they take, for whatever reason, and they start to combine these. So they'll say stuff like 1, negative 1 is a critical point, and negative 1, positive 1 is a critical point. And they start to kind of set up a permutation back to probability when you learn that maybe in higher algebra, where you have all the combinations with the 3 x values. You got to remember that whatever the x value is, that will cause you to get a single y value. Now maybe when x is 1, you do get x or y is negative 1 or 1. Maybe that's the case, but not in this problem. So you have to be very careful not to add critical points that are actually not critical points. So we have 3 critical points here, and we will now go ahead and test them in our formula. So we're going to calculate the second partial derivatives, and then we'll calculate d. So let's go ahead and test 0, 0 first. And when we test 0, 0, we want to calculate our second derivative. Actually, you know what I'll do is let's go ahead and do the second derivatives off to the side because we need this for all of them. So the partial with respect to x both times would be 12x squared. The partial with respect to y both times would be 12y squared. And the partial with respect to x and then y is just the constant negative 4. All right, so that's kind of our side note. Those are our second derivatives. All right, so let's go back and test 0, 0. Now remember, d is equal to the second partial, both with respect to x, multiplied by the second partial, both with respect to y, minus the partial with respect to x and then y squared. So that's our calculation that we're going to make for each of these. So d for the point 0, 0, if I was to take and plug in 0 for x and 0 for y, I get 0 for both, and I multiply, of course we get 0, minus, and then I'm going to take and substitute in negative 4, so I get the quantity negative 4 squared. This is, of course, negative 16, and that is less than 0. And if you look at our chart on the previous page, if d is less than 0, then what we have is a saddle point. Okay, first one is down. Let's try the next one. So we have 1, 1. All right, so our d will be, if I plug in 1 for x, 1 for y, then we have 12 times 12 minus, I still have negative 4 because that's a constant squared. So this gives me 144 minus 16. So this gives me 128. That's, of course, greater than 0. Now, if you go to your chart on the previous page, if d is greater than 0, then you look at the second partial derivative with respect to x both times. and we're looking at 1, 1, and we got 12. That is greater than 0. So then in my mind, what I think of is that when the second derivative is positive, the graph is concave up, and I envision a graph that's concave up. I sort of think about it in terms of single variable calculus, and that critical point we identified is a local minimum. All right, let's do our last point, which is going to be -1 and -1. All right, so our value D, again, I'm taking and substituting in -1 for x and y. I'm squaring both of those, so I end up getting 12 and 12 again. In addition, we get -4 because that's a constant, and so we actually have the exact same thing. And the second partial derivative with respect to x of -1, -1 happens to be still 12, which means that we have another local minimum. Okay, so that's what we've done for our 3 critical points. So we've been able to identify that 0, 0 is a saddle point, 1, 1, and -1, -1 are both local minimums. Obviously, we can go back up to our picture up here. Let me erase this. And we can see that that's really obvious as we analyze the surface itself. This little spot here is a saddle point. You can see that, based on one trace, it would be sort of this maximum kind of thing, and another trace, it would be a minimum. I mentioned that in the last problem where you were able to let x be 0 and y be 0, kind of analyze what it was doing. This is inconclusive when it comes to minimums or maximums because depending on the direction, it could be either. Therefore, it's a saddle point. We have 2 local minimums that happen to be the absolute minimums as well. We don't have to study that yet. And then the other thing I want to alert you to is the contour. We could get a sense of this, and we studied contours in the first half of the chapter. And when we look at the behavior of these 2 spots here, we can see that as we travel the contour plot, as we look at how the values are changing, we could probably guess just by looking at this picture that that's going to be a minimum of some sort, as well as this one, just because of the behavior and the values of the function itself. We may be able to tell that this is a saddle point by the contour. We may need a little more information though. All right, let's go on to the next example. All right, we're going to try example 4. This is the last one that I'll do in this video. This is just another local min or max value or saddle point. And so this is just additional practice basically at this point. You could try it on your own and then check with the video, or you could just follow along with me. Again, the first step is that we calculate the gradient. So we have 3x squared minus 12y and negative 12x plus 24y squared. We are going to go ahead and calculate the values of x and y for which the gradient is equal to 0, 0. So we have our first one and our second one. All right, and then it's just a game of trying to figure out how to solve this. What I think I'm going to do is take this second one here, and I'm going to set 12x equal to 24y squared, which means that x is equal to 2y squared, and then I'll use that over here in the first equation. So then what we get is 3 times 2y squared minus 12y equal to 0. So I have 12y to the 4th minus 12y. We can factor and solve. And in this case, I just get y is 0 and positive 1. And so then we go back into the kind of the place that we started. I'll change colors here. So we kind of go back here and say, okay, well, if y is 0, then x is also 0. So one critical point is 0, 0. And if y is 1, then x would be 2. So the other critical point is 2, 1. Okay, now our task is to identify what these two are. Are they minimums, maximums, or saddle points? So let's go ahead and calculate our second order derivatives. So our partial with respect to x both times is 6x, partial with respect to y and then y would be 48y, and then f of xy is again a constant. It's negative 12 this time. And our first step is that we're going to test 0, 0. So d is, at 0, 0, it will be 0 minus the quantity negative 12 squared. That's negative 144, which is less than 0. And we have a saddle point. Okay, next we're going to test 2, 1. And d is, let's see, that's going to be 6 times, nope, sorry, that's going to be 12. 2 times 6, and we get 48 and minus negative 12 squared. I don't really want to do 12 times 48 right now without a calculator. All I know is that that is positive because 12 times 48 is larger than 144. Okay, so that means that we're looking at the second partial derivative with respect to x at 2, 1, and that's 12, which is greater than 0. And so because we have that second partial derivative with respect to x positive and d is positive, that means that this will be a local minimum. Okay, I hope that that is a good start for you with regard to these first handful of examples. Next, what we'll look at is how to figure out an absolute max or min, and then we'll get into the next section, which is going to be another strategy to find those absolute values. Thank you.